We're going to be solving exponential equations. We're going to be solving some of them by equating exponents and some of them by taking a logarithm of each side. We're also going to be solving some logarithmic equations. Be sure to take good notes while you're watching the video. Remember that at any time, if you need to pause and rewind to review a concept, that you have the opportunity to do that. In this first example, we're looking at 9 raised to the 2x power being equal to 27 raised to the x minus 1 power. And the very first thing that we notice is that the 9 and the 27 can both be written as powers of 3. And so I'm going to take 9, I'm going to rewrite 9 as 3 to the second power, and then say that it's being raised to the 2x power. And on the other side of the equal sign, we'll say 27 can be called 3 to the third power, and we'll be raising that to the x minus 1 power. Now I have some nested exponents. I'm going to clear away my parentheses and go ahead and multiply my nested exponents. Turn the equation into 3 raised to the 4x power equal to, and on the other side of the equation, 3 raised to the 3 times that quantity, x minus 1 power. On both sides of the equal sign now, I have bases of 3 raised to a power, and so now I'm able to take the exponents and set them equal to each other. 4x is equal to 3 times that quantity, x minus 1. I'm going to distribute my 3, so 4x is equal to 3x minus 3. And then finally, solving for x, I'm going to subtract 3x from both sides. X is going to be equal to negative 3. This is another example where we're going to equate the exponents after we make the bases look the same. And so the first thing I notice is that 1/3 and also 81 can be written as powers of 3. I'm going to take 81 and express it as 3 to the 4th power, and then go ahead and raise that to the 3 minus x power. And on the other side of the equal sign, I know that 1/3 can be written as 3 raised to the negative 1 power, and then I'm going to be raising that to the 5x minus 6 power. I have some nested exponents that I'm going to go ahead and simplify by multiplying. And so we'll say that 3 is raised to the 4 times this quantity, 3 minus x. And on the other side of the equal sign, 3 will be raised to the negative 1 times this quantity, 5x minus 6. Now I've got two bases that are the same. Their exponents must also be the same, and so we can equate them. We can say that 4 times this quantity, 3 minus x, must be equal to negative 1 times this quantity, 5x minus 6. I'm going to use the distributive property and say 4 times 3 is 12. Minus 4 times x is equal to negative 1 times 5x minus 5x, negative 1 times that negative 6 plus 6. I've got a linear equation. I want to get x to sit by itself. I'm going to add 5x to both sides, and on the left side I'm going to have x. I'm going to subtract 12 from both sides, and then on the right side, 6 minus 12 will give me negative 6. And the solution to my equation, x is equal to negative 6. Now you try one. I have 8 raised to the x minus 1 power equal to 32 raised to the 3x minus 2 power. Hit pause on the video and see if we can solve the equation. I know that both 8 and 32 can be written as powers of 2. I'm going to let 8 become 2 raised to the third power, and then that will be raised to the x minus 1 power. And on the other side of the equal sign, I know that 32 can be written as 2 to the 5th power. And we're going to raise that to the 3x minus 2 power. Again, I have these nested exponents. I'm going to clear away my parentheses and say 2 is raised to the 3 times the quantity x minus 1. And on the other side of the equal sign, 2 is raised to the 5 times the quantity 3x minus 2. All right, I have like bases on both sides of the equal sign, and so therefore their exponents must be the same. I'm going to equate 3 times x minus 1 to 5 times 3x minus 2. And now we have a linear equation that we're going to go ahead and solve. 3x minus 3 is equal to 5 times 3 is 15x minus 10. Let's go ahead and let's subtract 3x from both sides. And so 15x minus 3x will give me 12x. And then let's go ahead, let's add 10 to both sides. And so negative 3 plus 10 will give me 7. And then finally, the very last thing, let's divide both sides through by 12. And so x will be equal to 7 divided by 12. Our solution, x is equal to 7/12. In this example, we're looking at 2 raised to the x power being equal to 5. This time, it's not possible to go ahead and express 2 and 5 with like bases. So what we're going to do, we're going to use a little different technique this time. We're going to take a logarithm of each side. We're going to take a logarithm because our x is stuck up into its exponential position, and I want to use that property that allows me to move exponents out of exponential position. So I'm going to start out by saying, let's go ahead, let's take the natural log of each side of this equal sign. I'm going to take the natural log of 2 raised to the x power and say it's equal to the natural log of 5. Now I'm able to say, let's let the exponent move down in front because of the property of logarithms that lets me do that. And so the equation becomes x times the natural log of 2 being equal to the natural log of 5. I want to get x to sit by itself, and so I'm going to divide both sides of this equation through by the natural log of 2. X is going to be equal to the natural log of 5 divided through by the natural log of 2. I chose the natural log so that I could actually use my calculator now to find a value for the natural log of 5 divided by the natural log of 2. And when I put it into my calculator, I get an approximation of 2.322. 2.322. We're going to be going ahead and using 3 places of accuracy with our decimals. In this example, I have 4 times e raised to the negative 0.3x minus 7 being equal to 13. Very first thing I want to do, I want to get e raised to the negative 0.3x sitting by itself. So I'm going to add 7 to both sides of the equal sign. And so 4 e raised to the negative 0.3x is going to be equal to, and when I add 7 to 13, I'm going to get 20. And the next thing I'm going to do, I'm going to divide both sides through by 4. On the left side, I'm going to have e raised to the negative 0.3x power being equal to, on the right side, 20 divided by 4 will give me 5. Now that I've got e raised to the negative 0.3x by itself, I want to get that x out of that exponential position, and so I'm definitely going to be using the logarithmic property that's going to allow me to move the exponents. I'm going to go ahead and take a logarithm of both sides, and since I have a base e already there, I'm going to be using a natural log. So we'll take the natural log of e raised to the negative 0.3x and say it's equal to the natural log of 5. Now I'm able to bring the exponent down in front, and the equation becomes negative 0.3x times the natural log of e being equal to the natural log of 5. But the natural log of e is equal to 1, and so I get to say negative 0.3x times 1 is equal to the natural log of 5. And finally, to get x to sit by itself, I'm going to divide both sides through by negative 0.3. X, it's equal to the natural log of 5 divided by negative 0.3. When I put this into my calculator, the natural log of 5 divided by negative 0.3, it is approximately, and using 3 decimal places of accuracy, negative 5.365. Now you try one. We're looking at 7 raised to the 6x power being equal to 12. Go ahead and hit pause on the video. Go ahead and work the problem, and then turn the video back on to check your answer. Because I can't write 7 or 12 as the same base raised to a power, I'm again going to go ahead and take a logarithm of both sides. I'm going to take a natural log of 7 raised to the 6x power and say it's equal to the natural log of 12. I'm now able to use that property that lets me take the exponents, bring them down in front of the logarithm. This will turn into 6x times the natural log of 7 being equal to the natural log of 12. Again, I want to get x to sit by itself. I'm going to divide both sides of the equation through by 6. I'm going to divide both sides of the equation through by the natural log of 7. And so x is going to be equal to the natural log of 12 divided by 6 divided by the natural log of 7. We're able to put this into our calculator. We want to be careful and make sure that we use double division, divided by 6 and divided by the natural log of 7. When we put this into our calculator, we get approximately 0.213. Now we're going to be solving a logarithmic equation. I have a log base 5 of 5x plus 9 equal to log base 5 of 6x. On both sides of the equal sign, I have the expressions that I'm looking to solve for stuck inside of a logarithm. I need to get them outside of the logarithm, and the way I'm going to do that is by using the logarithms as exponents. Because they're base 5, I'm going to raise both sides of this equal sign as powers on a base 5. So I'm going to have 5 raised to log base 5 of 5x plus 9 equal to 5 raised to log base 5 of 6x. I know that when I have a base 5 raised to a logarithm with base 5, then that expression is equal to what's inside of that logarithm. And so on the left side of my equal sign, I have 5x plus 9. And on the right-hand side, 5 raised to a log base 5 of 6x is equal to 6x. I now have a linear equation. I'm going to solve for x. I'm going to subtract 5x from both sides. And so 9 is going to be equal to x. The one thing I have to check and make sure when I get a value for x is to go back up into the logarithms, the original logarithmic equation, and make sure that the 9 is not going to create a domain problem for my logarithms. Remember, we're not allowed to put negative numbers inside of our logarithms. Their domains are x is greater than 0. And so when I check 5x plus 9 and I plug the 9 in for x, I definitely get a positive number. And when I check the log base 5 of 6x and I plug the 9 in for x, I definitely get a positive number. And so my answer, x being equal to 9, is a good solution. Now you try one. We're looking at the natural log of x plus 19 being equal to the natural log of 7x minus 8. Go ahead, hit pause on the video, see if you can work this problem, turn the video back on and check your answer. Because I have natural logs on both sides of the equal sign, I'm going to make both of them become exponents on base e. So I'm going to have e raised to the natural log of x plus 19 equal to e raised to the natural log of 7x minus 8. Because the bases of the logarithm match the base e, I know that the expression is going to be what's inside of the logarithm. So on the left side of the equal sign, I have an x plus 19. And on the right side, I have 7x minus 8. I've got a linear equation. I'm going to solve for x. I'm going to subtract x from both sides and end up with a 6x on the right-hand side. And I'm going to add 8 to both sides and end up with 27 on the left-hand side. I want to get x to sit by itself. I'm going to divide both sides through by 6, and so x is going to be equal to 27 divided by 6, and I could go ahead and reduce that x is equal to, and I can divide through by 3 and 3. 27 by 3 is 9. 6 divided by 3 is 2. And my answer, 9/2. And again, I'm going to go up and check and make sure that the 9/2 is going to create positive numbers inside of the logarithms. 9/2 plus 19 is definitely a positive number. And 7 times 9/2 minus 8 is also a positive number. And so I have no extraneous roots. X is equal to 9/2. In this example, I have log base 2 of x minus 4 being equal to 6. And again, I need to get my expression outside of the logarithm. So I'm going to make the logarithm become an exponent, and I'm going to put it on a base 2. So I'm going to write this as 2 raised to log base 2 of x minus 4. And it's going to be equal to, on the other side, 2 raised to the 6th power. Now that I have a 2 raised to a log base 2, I know that my expression is equal to x minus 4. And on the other side, I'm going to say 2 raised to the 6th power is equal to 64. I again now have a linear equation. I'm going to add 4 to both sides, and x is going to be equal to 68. My solution is x is 68. In this example, I'm looking at a sum of logarithms being equal to 3. First thing I'm going to do is use that property that's going to take that sum of logarithms and turn it into a logarithm of a product. So I'm going to turn this into log base 6 of 3x times x minus 1 being equal to 3. Now I want to get my expression outside of the logarithm, and so I'm going to make both sides of this equal sign be powers on 6. So 6 raised to log base 6 of 3x times x minus 1 is equal to 6 raised to the third power. On the left side of the equal sign, I now have 3x times x minus 1 equal to, and on the right hand side, 6 to the third power is 216. I now have myself a quadratic equation. 3x times x will be 3x squared. 3x times negative 1 minus 3x equal to 216. I'm going to subtract the 216 from both sides, and so 3x squared minus 3x minus the 216 is equal to 0. First thing I'm going to do is pull out my greatest common factor. I'm going to pull the 3 out. Left with x squared minus x minus 72. And then I'm going to go ahead and take my quadratic trinomial and unfoil it. And so it will unfoil into definitely x and x. Factors of 72 whose difference is 1, and so 9 and 8. And I'm going to want that 9 to be negative and that 8 to be positive. And so x minus 9 being equal to 0 means x is equal to 9, and x plus 8 being equal to 0 means x is equal to negative 8. Again, I need to go ahead and check and make sure, all right, that these are both going to work in the logarithms. And when I take the negative 8 and plug the negative 8 in for x, I can see that 3 times negative 8 gives me negative 24. And I know that the domain of a logarithm is greater than 0, and so the negative 8 is not going to be able to be used. It's an extraneous root. The solution that I do want to use is x being equal to 9. 3 times 9 is 27. And if I plug the 9 over here, 9 minus 1 is equal to 8. And so 9 works in both of my logarithms. 9 is going to be my solution. If you need to go back and review any of the concepts, be sure to take the opportunity to do that. We'll answer any further questions in our class discussion and practice using the skills presented in this video while working the problem set. Thank you.